Now it is high time that we go in medias res and look at what actors really are. Actors represent objects, and the actor model describes how these objects interact. And this is all inspired by how we humans organize, and it especially respects the laws of physics. What do I mean by this? Let us say we have a person here without a watch who wants to know the current time. Over here is another person with a watch. Now the first person will ask the question, what is the time? And the second person might just answer, it's 12:43. This is a simple exchange between two humans, and we all have done something like that before, so I hope everybody can relate to this example. But there's more than is visible at the surface. First of all, we take note that we transmit information by speaking and hearing the words. That means the first person sends a message to the second person. The second person then thinks a little bit, looks at the watch and replies with another message, traveling back on waves of sound. The two fundamental qualities here are, first of all, it is based purely on messages, and second, messages take time to travel from one object to the other. It is helpful to think of actors not as these abstract objects on which you call methods, but instead to visualize them just like persons who talk with each other. One thing also to note is that when we humans talk, we do not reach into each other's brains, for example by mind reading. We rely only on messages, and that is a very fundamental part of actors. More formally, an actor, as defined by Hewitt, Bishop, and Steiger, is an object with an identity. We know that from the second week of this course. And it has also a behavior, which we also already have encountered. And it only interacts using message passing, which is still compatible with the normal object definition. What is special about actors is that their message passing is always asynchronous. Let me illustrate what that means using another small drawing. We have an actor here. Let's call it actor A. And this wants to send a message to actor B. Actor A will send the message, and then it can just continue doing whatever it wants to do after that, without having to wait for the message to travel to B and to be processed by B. Especially, the processing happens in a different context at a different later time, as determined by the system where the actors run in. This is the most important property of actors. For this, we use the actor trait in akka. The actor trait defines one abstract method, which is called receive, and this receive returns something of type receive. Receive is a partial function from any to unit, and it describes the response of the actor to a message. Any message could come in, hence any, and the actor can do a lot of things, but in the end it does not return anything to its caller because the caller is long gone due to the asynchronous message passing. We implement the actor trait here in a simple class called counter. This one has one field, count, and it has a behavior. It must implement the receive method in the actor trait, and that must return a partial function. That's the partial function literal here with one case statement. And it matches the incoming message. So if we get a message with a string incr, then we want to increment the counter, which we do here on the right. This object is a pretty boring actor actually, because we can only send it this string and we never get any answer back, and we cannot determine what the counter actually is. Therefore, this object does not exhibit stateful behavior. If we want to make it stateful, we need to enable other actors to find out about what the value of the counter is. And therefore, actors can send messages to addresses they know. Addresses in Akka are modeled by the actorref type. So the addition here is we add another case, and if we get a tuple with the string get and something of type actorref, which we call customer, then we can send to the customer the count as a message. This is the exclamation mark operator, which is used to send messages, and it is pronounced tell in Akka. So customer tell count. In order to understand what is really happening behind the scenes, let me show you more parts of the actor trait. Each actor knows its own address. It's an actorref called self, and it is implicitly available. Actorref is an abstract class which has a method called tell or exclamation mark. And if you use the exclamation mark, that is the nice Scala syntax. Tell is more for Java. This takes an implicit argument. The implicit argument of type actorref is picked up from the surroundings. So if you use the tell operator within an actor, it will implicitly pick up the sender as being the self-reference of that actor. Within the receiving actor, this value is available as sender, which gives back the actorref, which has sent the message which is currently being processed. Passing the sender reference along with a message to the receiving actor needs to be done explicitly in other actor implementations like Erlang, but since it is such a common pattern, we devoted this one name in the actor to this purpose and do it automatically. Using this new power, we can make the counter actor look a bit nicer, so we just use the messages here and the sender is automatically picked up, to which the reply is sent. An actor can do more things than just send messages. It can create other actors and it can change its behavior. To access these functions, we need to know about the actor's context. The actor type itself only has the receive method, so it only describes the behavior of the actor. The execution machinery is provided by the actor context. Here you see an excerpt of the methods available on the actor context. These two are called become and unbecome. Each actor has a stack of behaviors, and the topmost one is always the active one. The default mode of become is to replace the top of the stack with a new behavior, but you can also use it to push and unbecome to pop the top behavior. You have access to the context within the actor by just saying context. Now let's see this in action. We can reformulate our counter actor into one which does not have a var. It will be a stateful object without an explicit variable. First, we need to define a method which gives us a behavior. This method takes an argument, what the state of the counter currently is. We start out with the counter at 0, the behavior counter of 0. If we get an inker message here, we change our behavior to be that of a counter of n plus 1. N first is 0, so it will be a counter 1. Within this counter behavior, at any time we can get a get request, where we just reply with the current counter's value. You can see here that this looks a bit like a tail recursive function because we call it inside itself, but it is asynchronous because context become evaluates what is given here only when the next message is processed. This is functionally equivalent to the previous version of the counter, but it has some advantages. First of all, there is only one place where the state is changed, and that is the call to become. And this is very explicit. The other is that the state is scoped to the current behavior. So there is no variable which we can leave somewhere in an unknown state. We always have the current state here. The last thing one can fundamentally do with actors is to create and stop them. The actor context has methods for that. First, actor off, which takes props, that is a description on how to create an actor, and a name, and it returns an actor ref. Also, each actor can stop other actors. One thing to note here is that actors are always created by actors. This means that they naturally form a hierarchy, because an actor is created by exactly one other actor. We will see that hierarchy and another one in the following weeks. And another thing to note is that stop here is often applied to the self-reference, which means that the actor decides that it wants to terminate. Let us try this all out in a runnable application. Of course, an application is also modeled as an actor in this model, so we call it main. This is an actor, and it uses context actor off to create a counter. We can say props counter to create an actor which does not take constructor arguments. And as all good things, it needs a name. We name it counter in this case. Then we send messages to this counter. In this case, we send it inker 3 times, and then we send it get. Remember that sending with the tell operator within an actor will pick up the self-reference as the sender. And since the counter will reply, we will receive it in this actor. Here in our behavior, we receive the count, which is of type int. We will print it out and then stop ourselves. I have loaded the counter actor code into Eclipse, adding the appropriate import of the actor trait, and with the implementation that you have already seen. The same for the main class, which needs the props in addition. In order to run this, we need to tell Eclipse how to run actor applications, because it currently does not know about that yet. So we create a run configuration. I have one prepared here. It uses the main class aka.main, which expects as its first argument the class name, the full class name of the actor class which is to be instantiated. Then if we run this, we will see that the count was 3. This printout was done by this line, so we received the count from the counter actor, and we received 3 because we incremented the counter 3 times. We could, for example, delete one of those lines and run the program again, and then the count is 2. Now we have seen all the basic things that actors can do. When they receive a message, they can send messages, create actors, and they can change their behavior for the next message. And this is all. This is the actor model of computation.